Okay, last day of this week. I'm not going to work on Sunday. This is pre-semester, so I'm just going to prepare for the semester on Sunday. So let's finish off this week. I'm going to do astrophysics. So the last time in astrophysics, we reached the three independent Gaussian distributions, which was just the components of our velocity vector, which was these three functions here, right? They're Gaussian, as you can see. This is just the normal distributions. Okay, and we reach those three. And from what we have here, we can conclude that if we want to simulate a particle that has a mass and a temperature, we can use this function here. And of course, this one will give us the probability for, let's say, v of x, which means that we have to draw three independent Gaussian distributions for each. So there's one Gaussian distribution for the component, for each of the components, of course. There's of course three. So you have to draw these three Gaussian distributions, right? Okay, we can do that. That is no problem. So we can actually do that in Python. I did just do that in writing because it's good practice. And of course, good practice is good. So you would just import a random. And then you have to initialize by using random dot seed. And then for obvious reasons, I'm going to, of course, initialize it with 42. This method here, seed, is pretty easy to understand. What it means is that you can think of this pseudo-random generator as a phone book. And each page has a given sequence of random generated numbers. But if you look at that page, of course, it's like a phone book. It's, of course, it's the same numbers, right? So it's the same sequence. So they're pseudo-random, so they're random enough for our case, but we can find the same sequence each time. So what is so good about this is that if you did some experiments, someone else could replicate what you were doing, right? Because they could use the same sequence of random generated numbers. That's why it's the same random numbers, right? We say pseudo-random because they are computer generated. They're not from nature. So if you want truly random, you have to use something like, with radioactive decay. Radioactive decay, that's actually truly random. So this one isn't random. It's pseudo-random, but that's enough for our case. And to get the number for a Gaussian distribution, you just use number. We can write number is equal to random, and we have the method Gauss. And we, of course, the parameters, of course, the normal distributions. That's, of course, just the mean and the standard deviation, like that. Neat. Okay. So now we finished the velocity components of gas particles. And now let's move to the next section, which is the absolute value, it's the absolute velocities of gas particles. Absolute value is actually what we need. So we're not interested in the components. Instead, we're of course interested in the absolute values. So why is that? I don't care about what direction the particles are going. I care about creating a total momentum, right? I care about the total thrust that we can do, because we are, of course, simulating a rocket engine. I just want like something like total pressure. That's what I want, because total pressure, more momentum. If I threw something one way in space, I go the other way, right? Newton's third law, or conservation of momentum. That is what we want. So I don't care too much about the components here. I don't want the velocity vector. I just want the velocity as an absolute value, right? Okay. Very neat. Let's see. Yes, and of course, this formula, or you say this distribution formula, is different than we have. So I just show this from the book. It's actually this guy here. We're going to deduce that later. So, but for now, we just have to accept it. It's very close to the same. It's another version of that Maxwell-Boltzmann distribution, right? There are multiple versions of that. I also made maybe a mistake last time. I actually drew this distribution last time, and I hope I didn't say that this one was normal, because it clearly is normal. I think it's chi-squared, but we'll get back to that. So let's go back. But this distribution just tells us what is the probability that in some interval from v to v plus dv, as you see here, that particle has a certain velocity and that particle has a mass and temperature, right? That's what we want. Okay. Perfect. Let's move on. Now we also have another function that we're going to use now. So the function we had was p of v. But p of v is just density. What we actually want is the number density. So number density is pretty easy. Number density function is just number of particles times pv, like that. So that's the number density. So that's actually the number of particle per unit volume. So that's just the number density function. Okay, pretty neat. Okay, and now we can move back to that graph that I wanted. So this one has some problems in terms of what we did earlier, because for first, this one is not Gaussian. As you can see, it's clearly skewed to the left. Also, for absolute value, there's no, of course, there's no negative value. Like we had 0, so they cancel each other out. So we got 0 as the mean value, but of course 0 is not the mean value, it's just 0 velocity. That makes no sense. And standard deviation 2, we don't know. Okay. So we can actually, even though we don't know the mean value, we can actually find it. It's not that tricky. We just have to use one trick that I actually spoke about last time. So if I want the mean value, since it is a distribution, we can of course use the law of large numbers. So I could just 0, infinity, and then n, p of v, and then dv. And there we have it. And of course I have to insert this distribution there, right, if I want that. So if you can go back here, you can see that they did that, but this one should be pretty simple. I should have just v. Of course, yeah, I did a mistake there, but the idea is still the same. Of course, I shouldn't use the number density. I just want the v there. That makes no sense. Yeah, you can see clearly that I made a mistake, because this is the same. Of course, I need the weight and the probability. that was not good. I should, of course, need to be there. Okay, but otherwise it's correct. Okay. All right. Now let's move on, and of course now we have finished up with Gaussian statistics. But now the next thing here to do is that we of course need some physics concept. We're just doing statistics. So of course this is particles and gas. Of course it's thermodynamics. So we need some concepts. Of course the first is pressure, force over area. What is it? Of course, if I use this Apple pen, this doesn't hurt too much. But if I have the same force and I had a needle, for example, this one is a little bit not like a needle, but this hurts more, right? Because the area is of course smaller. But we don't care too much about that. We care about a cylinder this time. That was way too big. Let's do it like this. That makes more sense. Yes, that's a better one. Okay. So we care about this cylinder here. Now this cylinder has some area here. This is the area. It has a gas, and in that gas, of course, there's particle with momentum, like that. My arrows are pretty stupid, but who cares? And they are bumping into each other, bumping into the wall, etc. But we only care about this area here. That's the focus. Okay, and also I need this one as well. So we need just the distance here that the particles travel, which is just delta x like that. Okay, so the particle here will of course bump into each other and bump into the wall. We are going to have an idle gas of course later, so it's an elastic collision, so there's no loss in terms of kinetic energy. Also, there's going to be an elastic collision with the wall, so also lost no energy there. So if there's no energy loss, of course, the system itself is conserved. And that's pretty easy, of course. If I want to add energy to a system, I need to heat it up, I add energy. And if I remove energy, temperature, for example, moves away. But in this case, they don't. Like, they keep having the same kinetic energy, they have the same temperature, of course, the system is conserved. Okay, perfect. So now let's move to the equations that we want. So we can start off by having a wall, and we can think of, actually that's the wall that we want, but we can think that a particle is approaching our wall. I should have that in blue just to make this clear. That's our wall. And we can think of our particle here with momentum p that's approaching the wall. The components is of course just p of y and p of x, like that. And if that particle keeps on moving, it will hit the wall. And that collision right there is actually pretty neat, because again it's elastic, meaning too also that the angle here is just the same both ways. And the only thing that's changed is actually just the direction, not p of x. So if again just write this again, the size here is pretty stupid, but who cares? P of x and p of y. So the only thing that actually changed was the direction, and that's just in the x direction. So we have, before the collision, we have p of x, p of y, but after the collision, we have minus p of y, minus p of y, minus p of x, and then of course p of y, which means that the total change in momentum is 2px, right? Okay. Now we can write the force, and the force, as Newton would have written it, is dp over dt. This can be assumed to be delta p and then delta t. Delta t is the amount of time all the particles has hit the wall, and we know that the top one here is just 2px over delta t, like that. Okay, we can model this further. So I know that the particles has to travel delta x, right? But as a bunch of particles, one batch has traveled and hit the wall. One batch is actually leaving the wall, right? So it actually means that when in the total time for the particles, all the particles hit the wall, it's actually the travel distance, is actually 2 delta x, right? Because you need two batches like that, for example. Okay, that means that, let's say in just delta x, we instead have delta t prime, okay? Which means that delta t is equal to delta t 2 times delta t prime, right? And delta t prime, remember that the particles will have the velocity v of x. So you'll have 2 delta x and then v of x, right? And this can, of course, be rewritten very neatly, because we have delta t is equal to that. Then we can use what the force is. The force was just 2px over delta t, and just some simple algebra, 2 goes away, and we have px vx over, of course, delta x, like that. Pretty neat. Okay, now we're getting close. We want, of course, pressure. So let's move this on. Okay, this is okay. Let's see. Yes. Okay. Yeah. Okay. So in the same way that we had a distribution for velocity, there is also, let's see, I had also, before I go there, let's see. Okay, I need one before I go there, I need one thing more. So, there's one more property we have as well. Actually, remember, we are interested in the absolute velocities, so v squared is of course equal to vx squared, vy squared, and vz squared, like that. Nice. But since the particle doesn't favor any directions, of course, v squared is the same, or v squared is the same as 3 vx squared, like that, meaning that vx is the same as v divided by the square root of 3, and since we have no relativistic effects, of course, momentum and velocity relates pretty neatly, and of course we just have this relationship here as well. Cool. That should work, and now we can change our equation to, of course, just be P times V for the force divided by, of course, what did I do now? Of course, yeah, and then 3 delta x, like that. Very neat, and now I can go what I wanted to say. So, of course, we found that there's a density, or not found, but there's a density function for the velocity, right, the absolute value. But of course, again, we can relate momentum pretty easily. And then that means that there should be a density function for momentum as well, right? Okay. But this is just density function, right? So we can do some really nice trick here. So let's say I instead want the total number of particles, right? What I can write then, the total number of particles with momentum, I can write then as n, let's say n of p, right? And how can I write the total number of particles? The total number of particles is of course just, let's see how I can think about this. With momentum, yes, that means that, yes. Area times, yeah, of course. So this is total number of particles. Now I can write this by just using that n of p, right? And remember, n of p is similar to v. N of p just represent, it's actually the same as n of the probability function of p, right? And of course, that represents the probability that a particle has a momentum between p, p plus dp, right? That is what it has. Now we want the total number of particles. That's just the density. And of course, in order to get the rest, we just need a volume. And the volume, of course, is just A delta x. Pretty neat, okay? Then we can write this as n of p. A can just stay there. Whoops, that was not good. N of p, A can just stay there, and delta x, we can actually do some, maybe I just keep it, yeah, I keep it like that. That works, okay. Let's model the force. Now, the total force, dF here, because that's just change in force, that the particle exerts on the wall is of course just dp over A, but now we have it because this was the total momentum from all the particles, right? So we just have, that will be, no, have I done that correctly? Am I thinking about something else? No. That should be correct, isn't it? Yeah. The total number of particles, yes. Okay, so now I have, I just need that force equation, right? Right, because that's just for one particle. I just have the force equation. Yes, I just have the force equation for one particle, and now I need the total number of particles. Right. That's just n of p, a, n of p, and then A, and then of course delta X, and then of course we need some D, so I have dP. I need just of course some change here. That sounds so dumb. Okay, yeah, so that should be alright. I can just get rid of delta X and delta X. Perfect, and this expression here now is just 1/3 P V, then I have A N of P, and then of course dP. Perfect. And of course, if I now want D pressure, this expression gets even better. I just get 1/3, then I have PV, A goes away, I have N of P, and then dP in the end. Perfect. Very neat, right? Now we have pressure, the change in pressure, the total change in pressure exerted by the particles on that wall, right? That is what we want. Okay, so this is just change in pressure. I need the total, of course, my mistake. And the total is pretty easy. That is just if I integrate this function from 0 to infinity, then I get the total pressure. So P is just the integral 1/3 0 infinity P V N of P, and then of course dP. Come on, please say that's correct. Okay, nice drawing. That's correct. Correct as well. Correct. Correct. And then we have, is my argument here correct? It is. Total, yes. And then we have this guy. Yes. Perfect. Okay. Now we are pretty good. Okay. Very good. Yes. Okay. Yes. Now we can find the pressure. All we need to relate here is, of course, P and V. And now we have the pressure. Okay. Okay, this is our distribution function, of course, etc., etc. We don't need to care too much about that. But there's another question that arises now. And that is, we need, of course, to know the initial position of the particles. And that's an exercise. But the question that arises is the distribution they follow. Which is that? And that's pretty easy. They follow the uniform distribution. Why? Because a particle doesn't favor any position. They're just in cylinders where they start is just completely random, but X doesn't have anything to say over Y, of course, so it's uniform. So to use that, you just use the same thing like we did. You import random, initialize with the seed value, and then you could say that the number you want, so number, is equal to random dot what was it? Oh my days, uniform. It's a uniform, of course, uniform. And then of course it has to be between something, and that's just x1 and x2. Like that. Neat, very neat. Okay, now we're nearly done. Now the next thing is that our pressure has P, not V, so we just that remember from our function we have spoken that we have some density function N of P, but we haven't seen it. So we're going to deduce that later in the course, but actually now this is just from our velocity function. And of course you just make some changes with mass and then you're good. So I can just show it here. So there's that function that we had P of V, and of course to get with P you just add mass. That's it. There's nothing special about this at all. Okay, and that's just it. I can just tell her because we're nearly finished. But this actually, if you go through this and the calculations, you will see that this is actually the ideal gas law, right? That's perfect, because now this equation tells us if we increase the pressure or the temperature here, now to increase the pressure in a gas, all we need to do is increase the temperature or the density, which is what we want, because if this is our rocket, there's a satellite, there's a fuel tank, what we do is that if we increase the pressure, of course, if we increase the pressure, let's say I have some box to increase the pressure, of course the momentum will be bigger. Bigger momentum will throw particles one way and the rocket will go the other way, right? That's the whole idea. Perfect. And the next here, I don't think we need to speak too much about this. They just explain what I just said here, the next. And of course, we will have millions of particles. They are hard to simulate. So instead of simulating this whole combustion chamber, we just split it into smaller boxes, right? We can do that. It's still the same. You just have to multiply by the number of boxes later, right? So that's just it. And in the end, of course, you have to beat escape velocity. That's it. Or you have to reach escape velocity, because you have to not beat escape velocity, you have to beat gravity, right? You have to beat the gravitational pull of the planet, which means that you, of course, have to reach escape velocity. Okay. Perfect. Now we're finished with this section, and I'll see you next week.